Hello and welcome to the AI for Predictive Smart Maintenance seminar series. My name is Madhav Misra and I am hosting this seminar series. And I also like to mention those who are the first time at this seminar series. I would like to say that this RISE is organizing a seminar series bi-weekly. So please feel free to share this seminar within your network if you believe that someone is interested. So today we are honored to have a speaker from Cranfield University, UK, Dr. Ivan Petronin, who will share his work on the topic of ensemble-based diagnostics of multiple fault in rotating machinery operational data. Let me introduce about a brief introduction about Dr. Ivan Petronin. He is a senior lecturer in signal processing for autonomous system at the School of Aerospace, Transports and Manufacturing of the Cranfield University, UK. He has extensive knowledge and experience in applied signal processing for various industrial and civil engineering applications related to rotating machinery and more recently related to autonomous system application for detection and classification of weak non-stationary signature in area of acoustic and ultrasonic and vibration signal in complex environment. So Dr. Ivan Petronin leads the Signal and Autonomous Group at the Center for Autonomous and Cyber Physics System at Cranfield University, and focusing on activity support, operational aspect, and application of autonomous ground and aerial systems, including localization, surveillance, and unmanned traffic management and digital aviation research and technology center is known as the Tech. Ivan is leading and contributing to several projects in the area of applied signal processing, including AI and ML, for autonomous aerial and the ground system application funded by UK government and European Space Agency. So general information, as most of you already know, that the projection will take around 30 to 45 minutes. Afterward, we will have the opportunity for question answer. And as mentioned beginning, is we record the seminar, share it with the audience, and upload it on our YouTube channel. So you can still watch the workshop offline if you miss it. Welcome, Ivan. Now you have the floor, and we are excited to listen to your talk. Please go ahead.
Thank you very much. Let me share my screen now. Okay, coming through?
Yes.
Yeah, perfect. So thank you very much, Madhav, for introduction. So today I would like to talk about our experience in using Ensemble Learning for diagnostics of multiple faults for rotating machinery. I'd like to start with a little bit of introduction of the background of the problem. Probably most of you are already familiar with the scope and context of that problem and the challenges as well, but just to bring this to the common level. So first of all, machines obviously may have multiple faults present in the system where a combination of the faults is usually one of the most challenging problems. The structure of the faults is quite well investigated, so we know that some of the faults are appearing more frequently, some of them are probably less frequent. However, the problems is typically coming from multiple issues when we need to deal with faults which may be masking each other or preventing detection even of some of other faults. Historically, the problem was fairly well investigated, starting from the single fault appearing in the components of rotating machinery, where bearings, gearboxes, and shafts, typically representing those parts contributing the most to the frequency of the failure mode occurrences. And historically, the development was going through multiple stages, starting with application of advanced signal processing techniques, combination of these techniques, and then going towards machine learning more and more, where recent trends are focusing on application of deep learning techniques for diagnostics of the faults. The problems here are coming from the point of view, again, detecting and diagnosing multiple faults, where each of the fault condition may have inherent challenge in terms of detecting it. So it is fairly difficult to suggest a single technique or even single, so if we start speaking about signal processing technique or single machine learning technique, which is easily able to deal with multiple faults and recognize these faults in terms of providing us with diagnostic information. Therefore, in many cases, the solutions were in feature engineering, where someone was deciding what features can be used for the diagnostics, for example, covering the whole possible range of problems appearing. However, because of variability of the conditions and variability between the components, so typically this creates a challenge in terms of using this information effectively. One of the ideas in terms of improving the diagnostics process was to use ensemble learning in terms of creating system which might be more flexible and more scalable in terms of dealing with multiple fault conditions and potentially going into multiple faulty component stage as well. So let us talk a little bit about ensemble learning. So what ensemble learning is about. In general, the main concept behind ensemble learning is to use multiple classifiers which are able to provide you with information, maybe not of the highest quality, in terms of the particular condition which we would like to classify. So here we talk about faulty conditions or the fault itself, which we would like to detect using classification approach. What is the main idea here is that when we use a single technique, it tends to make mistakes, so single classifier. When we have multiple classifiers, they also make mistakes, but under certain conditions, the mistakes may not be the same between the classifiers. And therefore, combining these techniques together, it might be possible to improve the quality of the decisions, because we can consider a combination of techniques utilizing the best information from each classifier for making decisions. In general, ensemble models consisting of several base models or base classifiers or base learners, the terminology is quite flexible here, which are providing information about the problem they detect. It may be same problem, they might be different problems as well, which we would like to analyze simultaneously, for example. And then there is a way also we can combine the information from these classifiers. The classifiers can be of the same type, and here we can speak about homogeneous models, where we have n classifiers of the same type, like support vector machines, for example, or neural networks whatsoever. Or they can be heterogeneous as well. So we can think about using different algorithms, not necessarily of the same type, which might be selected according to their particular properties or suitability to the problem we are going to solve. And then the decision should be combined in a way where multiple approaches were proposed in general. So if we look at the ensemble learning approaches, there are three most well-known groups exist implementing ensemble principle for the learning, which are related to parallel implementation or bugging techniques, where we have a number of classifiers arranged in parallel, so making decision at the same time. And typically we manipulate data with that approach, and then we use weighted average in terms of combining the outcomes of these classifiers. Boosting techniques related to a principle of sequential learning, where several base classifiers are obtaining information from each other in sequential manner with redefined weights. And another technique, another group of approaches, rather, which I would like to discuss in a bit more details today, is related to stacking and blending. So what is the principle of stacking and blending? So you can see an architecture here on this slide. We typically deal with several base classifiers, again, as for most of the ensemble learning techniques. However, in this case, we also have a second layer, which is presented by the classifier, which learns the quality of the outcomes from each of the layer 1 classifiers. For generic stacked approach, stacked ensemble approach, we need to arrange data in k-fold, so similar to the cross-validation problem, train the base classifiers, and then train the next layer of meta-classifier with the out-of-the-fold set of data. So in that case, we train the meta-classifier in terms of understanding where each of the classifiers having some advantages or disadvantages. And in that way, we provide a more smart or more intelligent way of combining information from individual classifiers in comparison to sequential or parallel ensemble learning approaches. So I would like to illustrate application of ensemble learning in the form of stacked and blending type of approaches for several common problems related to diagnostics of bearing faults, gearbox faults, and also shaft faults. So I start with a bearing diagnostic case where the data set was used is a public data set combining information from two bearings collected with the accelerometer with 7 faulty conditions represented in this data set. Along with the faulty conditions, so you can see some examples of a difference between the faulty conditions using very simple type of signal processing technique illustrating it. In addition to variability in fault conditions, the data set also provides variability in terms of load types, shaft speeds, and also it provides basic information about the bearings as well. So we have frequencies related to the faults, and over a number of runs, it is ensured that we have a good robustness in terms of representation of the faulty conditions in this data set. So what we have explored in first place is application of ensemble learning in a form of a modified stacked generalization approach. So here, instead of a stacked generalization, we implemented blending ensemble approach. And the difference between the two is that instead of using out-of-the-fold validation for training the meta-classifier, blending ensemble is using a different approach where the data is split into a few parts, and the meta classifier is learned, is trained using validation data set rather than out of the fold data set. So it provides an improvement in terms of the accuracy of the classification. However, in some cases, it may be leading to slightly increased risks of overfitting. The architecture of the proposed approach is shown here. What we have proposed is to use 3 identical types of the base classifiers presented by convolutional neural networks. You can see it here, which are taking information from the feature spaces. So we organized 3 feature spaces in a special way. So each feature space is provided by a dedicated signal processing technique. So here we utilized 3 of them: spectral kurtosis, cyclic spectral coherence, and bicoherence. And finally, the decision is made by a meta classifier, meta learner, which is presented by support vector machine technique. And we also explored some variability in terms of meta learners as well. So why we selected these 3 techniques? It was some process behind, which we presented obviously in the paper. So just to come back, you can see the link to the journal paper which was published. So the presentation is based on the published information. So in terms of getting a bit of extra details, please feel free to refer to these papers. In terms of technique selection, it was a process behind, which was based on analysis of the strengths and the weaknesses of each technique. So this information generally available, so it is well known. Therefore, consolidating of that information provided us with understanding what we can obtain as a benefit from a combination of various techniques. Of course, initially the scope was much wider, but finally we converged to these 3. In general, we know that, for example, cyclic spectral coherence is one of the very good, in general, techniques. It can be used for multiple applications. In particular, it is fairly effective for bearing and gear fault detection problems, also in the presence of non-Gaussian noise. Spectral kurtosis and bicoherence have their niche applications as well, such as, for example, a refinement of information about frequency content of the problem for spectral kurtosis, and also phase coupling between components and the sensitivity to modulation context in the data in the presence of noise as well for bicoherence. So that was the basis for technique selection, and here we have performed some visualization, also understanding the difference between good and faulty conditions for the selected data set. We can see that all techniques we have selected are providing us with a different type of information and providing us with the insight into the faulty conditions which are present in the data set, but in different ways as well. Right, so implementing these techniques and training individual classifiers on the training data. So again, this is a blending type of application for Ensemble Learning, where we train individual classifiers or base classifiers on the full training data set. We have obtained these large confusion matrices, which are given here just for illustration purposes, with interesting observations as well. So what we can see here is that in general, we observe that information about the errors presented in different ways between individual classifiers. So we typically have some variability over here, And for example, if we take a particular condition, we see that the quality of decision making and the error rate also is changing between individual classifiers, which means we have certain independency between the outcomes of these techniques. And this is exactly what is required in terms of creating a good ensemble of the realizations. Of course, we can also observe that each of the techniques is providing us with fairly good performance on their own, probably a bit less for the bicoherence type. However, it's still over 90% for all three classifiers. And this difference in terms of individual outcomes between the classifiers results in enhancement of the performance. So when we can see the same classes for the combination as an output of the meta learner here, we can see that the error rates are reduced for all classes. It's also interesting to see that the errors which we observe, remaining errors, are related to those classes or labels of the faults, which are presented almost uniformly between individual classifiers, such as, for example, in this case. We have performed also a comparison between different implementations of meta-learners and two techniques which we analyzed, decision tree and support vector machine. They were still providing improvement over individual classifier using single signal processing technique, and support vector machine was having an edge over decision tree in that respect. So we finally used support vector machine as a classifier. So here there is a summary of the performance of the proposed model for diagnostics of 7 faulty conditions of bearings on this public data set. And what we observe is that the performance we have achieved, 98.5% in terms of the accuracy, is fairly good compared to other type of techniques proposed for fault diagnosis. So here in the table below, you can see a summary of other techniques utilizing machine learning for diagnostics of the faults in bearings, or in more complex cases when bearings and gears, for example, are used. And we can see that our proposed method is fairly effective in terms of these state-of-art solutions. Of course, considering that gearboxes is typically providing us with a lot of faulty conditions because of the nature of the operation, the gear data set and application of the approach on the gear data set was the next target for us. So here, again, we propose to utilize conceptually similar architecture where we use 3 branches of the base classifiers, each supplied with information from dedicated signal processing technique, and with meta learner which learns about the outcomes of these base classifiers. However, the pre-processing was modified in that case, where we utilized time synchronous averaging and residual signal extraction to supply information to signal processing techniques. The gear dataset here is presented by another public dataset, which is called PHM09. In this case, we have multiple faulty conditions. So they are labeled in the dataset as SPUR1 and SPUR8, so 8 faulty conditions. Some of these faulty conditions are related to multiple faults from multiple gears as well. So not all of these conditions related to single fault. So the types of the faults and number of the faults is varying here. And of course, there are some other conditions in terms of the speed, the load, and so on, which are making this data set usable for evaluation purposes. Right, so we have performed some adaptation of the parameters for all three signal processing techniques, selecting the parameters which are improving the classification performance. And again, here you can see examples of how the good and faulty conditions of the data set are represented through the selected signal processing techniques. Again, selection of the feature space is fairly important. Therefore, we did this analysis beforehand in terms of evaluating how we can work with the information available from the signal processing techniques. We can see that there is a difference between conditions presented in all techniques. Again, representation of those differences are varying between selected techniques. And this is good from the point of view of making ensemble effective for the damage diagnosis. Again, we have evaluated performance of individual classifiers separately before going for the combination, and we can observe very similar behavior where the errors classifiers making on each of the type of failure conditions are different. So in general, we have noticeable variability between individual classifiers in terms of the errors they make. And this actually helps to improve, again, the output performance and allows meta-learner actually effectively understand where each of the individual classifiers can provide better information about faulty condition. So as you can see here, we were able to achieve fairly good performance overall. For example, if we compare individual performance of each of the classifiers here, so again, just to remind, each of the classifiers was connected to its own feature space. And we can see that performance of the combination using support vector machine as a meta-learner is significantly higher than each of the performances from individual classifiers. Again, we have performed some comparison, and you can see at the bottom the link to the paper, which provides all related information. We can see that the proposed technique is fairly good in terms of performance, comparing other solutions proposed for the similar problems. So in a number of cases, we have an improvement in terms of performance over state-of-art techniques. And the last part of our exercise was related to application of Ensemble Learning to shaft problems. Again, the consideration was given to public data sets in terms of obtaining information from the shaft using multiple faulty conditions and variability in load and speed conditions as well. So here you can see a description of the data set, and it is available on IEEE data port website. So if you would like to have a look at it. The same approach was utilized. We used, again, same three types of feature spaces provided by signal processing techniques: bicoherence, spectral kurtosis, and spectral coherence, cyclic spectral coherence. And again, we can see variability in terms of the information these feature spaces carry in terms of having faulty condition present or having normal condition present. Again, this is seen as a positive indication that we should have good performance for ensemble technique implementation. The information again was obtained in a form of individual classifiers. The performance was fairly well. We can observe a little bit of indication of overfitting in certain cases. For example, the test accuracy was lower in comparison to validation accuracy by approximately 5%, which might indicate a little bit of overfitting. However, overall, the performance was still fairly high, around 90% and above. And because of the similar behavior between individual classifiers, we can observe that using a meta-learner, again, here the comparison was performed with two types of meta-learners, decision tree and support vector machine. We can see that the combination allows improvement and significant improvement in terms of the quality and performance of the decision we make. The comparison we made again here related to several works, and here in this table we show results, the titles of, apologies, we show the titles of the papers utilizing the shaft data sets. We can see that performance of the proposed solution is fairly high. So we can see in the cases when we deal with multiple folds, which is in general more complex than having a single fold, because we have variability between the folds, and some of the folds, if we can go back, for example, here, some of the folds are detected with 100% accuracy here. So we see the average result of 98.7% as very good result compared to other existing solutions. Finally, some early results in terms of integrating the models, because obviously the next step is related to integration. So how we can deal with information from all components going through into the Ensemble learner for fold diagnosis. So similar approach again is used here with more complex pre-processing stage, because it requires a dedicated pre-processing for multiple feature spaces. We have performed more extensive optimization here, because in general, for each of the components and for each of the signal processing techniques resulting in the feature space, we may want to have an optimized set of parameters. And also we need to understand how to combine these parameters together. So because we are not aiming to train this separately for each component, so it is supposed to be a universal framework suitable for multiple components. So optimization have been performed, and we can see that it is possible to select parameters which are suitable or leading to insignificant degradation in the performance for multiple components and multiple fault conditions across signal processing techniques. You can see some examples of the feature spaces generated by the signal processing techniques when we vary parameters from optimal to suboptimal case. And the application have been done. So this is early result. It's not a final result. The application have been done, and what we have done so far is we performed visualization of the representation of the faulty conditions in a reduced dimensionality space. So here we deal with 16 faulty conditions for 3 different types of components. And at the first step, we visualized how these conditions and the data corresponding to these conditions can be represented in the original data set. Of course, we cannot see this in multi-dimensional space, so we used a statistical embedding technique for visualization purposes. what these results, which you can see here in the top left corner, tell us is that for individual feature spaces with corresponding individual classifiers, we have overlaps between the clusters of the classes. And overlaps means we cannot always recognize them effectively, even using meta-learner. So that means we need to use the meta-learner should be improving that information. And we can see confirmation of that in the result, which is coming from meta-learner. This is a panel D here, the bottom right figure in the block. We can see that separation between the clusters representing the faulty conditions is much better when we utilize the proposed approach. And this is confirmed by initial value of the accuracy we obtained for a combination of bearing, gear, and shaft faulty conditions, which were combined together, where we reached almost 99% accuracy overall. And again, our early comparison with existing works indicates that we have fairly good results compared to other state-of-art solutions. Good. So what we would like to conclude here from this comparative study is that using ensemble learning, we can actually achieve a few interesting outcomes. So first of all, we can adapt the decision-making process and fault diagnosis process to different features present in the data. And we are utilizing multiple signal processing techniques for that. So in a way, we are approaching data fusion or information event fusion method, where combination about features representing the faults are combined through the ensemble learning technique. Using this technique, we also allow for more intelligent way of dealing with information from individual classifiers. So we are not simply combining them, for example, using majority voting or weighted average, but we actively learn where, in what part of the feature space, individual classifiers providing advantage in terms of improved performance. And we utilize that information, which, as we can see, results in more efficient process of fault diagnosis. So finally, this type of approach is very promising. It may help to improve the safety of the systems, and you can see here an example at the result of consequence of the crash of the helicopter, which was one of the very prominent examples of the gearbox-related crash of the complex machine, which led to life losses. So using these type of approaches, we can minimize such tragic consequences. And of course, this work is very far from completion. This is still work in progress, where multiple improvements can be done, and we're actually actively working in this direction in terms of providing further improvement and enhancements into the process and making it more comprehensive, robust, and effective. And this is it for this presentation. Thank you very much.